So, chromatography. So to wrap up this course, we were going to give you a real taste of instrumental analysis, but pretty much only how the lecture portion works, because we're not going to be able to do anything and have time to do anything in the lab. But pretty much how this is going to work is you're going to hear me talk about a lot of stuff, and you're taking notes and things. And then when we come to class, after break here, there'll be a quiz. And the quiz is on pretty much what we talked about. So you want to make sure you take good notes and review it before the quiz, because it's not problem-based like what we're used to. Okay. So the first part that we're going to discuss is chromatography. And what's the big deal? Well, pretty much the whole world, when it refers to chemicals, they mix, right? And it'd be nice to know what you have in the mixture. That'd be one good thing to know. It'd be nice to know how much, right? How much you have of everything in that mixture. So, or what if you made something? I mean, is it pure? There's so many different applications for chromatography. And that's pretty much, I think, why it's not I don't think that statement is overstated at all, that it's the most used and versatile technique in analytical chemistry. So as a kind of a little flow diagram as to what's happening is this little picture. And at the top, so everything is supposed to be moving this way. And at the top you have this jumble, right? And you just dumped in everything, okay? And then the magic happens. Notice how these things start separating out. They start traveling down this path at different speeds. And looks like the blue guys are the slowest. All right, something's going on, then these guys, and then these guys. It takes a while, and if you do everything right, yeah, they start separating out on their own, it seems like. Then you have to have some little detector that detects these things as they come off. And sure enough, over time, so you detect things over time, and you'll get your peaks. Right? It looks like the little green compound came off first, and the orange, and then the blue, and so you get a different peak for each one. So literally, you could have stood here with a beaker at the bottom and just collected the pure stuff, right? And it would actually work, and they do that. So the detector has to be something that's going to detect. It could be light, it could be mass, it could be a number of different things. Some detectors destroy their sample, others don't. But this needs to be something that's going to be characteristic of everything that it's trying to detect. Okay, otherwise I guess you'd pick a different detector. So some general terms here. We have I forgot them. Well, you're gonna have to use your imagination. Here's my vis-a-vis markers, right? Well, they're kind of, just pretend. Okay. So what's the idea of vis-a-vis markers? What's so special about them? You can write with them, right? And you erase it with water, right? So the dry erase markers aren't really vis-a-vis markers, right? But vis-a-vis markers are, you can write on overhead transparencies. I think we're the last, you guys are the last generation that even knows what an overhead transparency is, right? But, so vis-a-vis has to be going out of business, I would think. But anyway, so vis-a-vis markers. So let's say, I don't know, something in these vis-a-vis markers is getting Naya sick, right? And it's the green ones. Something in there just, every time she gets the green mark on it, it's all rashy or whatever, right? So let's do some chromatography. Let's separate out all the different components. So the idea is so that's what I did on here. Now if you're going to do chromatography on these vis-a-vis markers, I get you started on the thinking. I put some markers on there, right? I have blue, black, red on some pieces of paper. And then I've got a green permanent marker, a blue permanent marker, and the green vis-a-vis. So that's what all this stuff is. What is the paper called? What's the technical jargon for it? It's all those 5 million words that you wrote. Starts with an S. What phase? Stationary phase. So you have to have some type of stationary phase. Okay? And that's my paper. Now, what else do I need to do chromatography? And this is all types of chromatography. There's very specific forms. You've heard, if you've seen the forensic science shows, there's gas chromatography, liquid chromatography, ion chromatography, and there's several others. But that's the thinking. But all these types of chromatography have a stationary phase. And they also have a mobile phase. Okay. What causes the separation? Does anybody know? Where does the magic happen? Where does all this, ooh, he's winning, green's winning, then orange and blue. Where does all that happen? All right? Is it the mobile phase? Something's got to be physically doing something to slow these things down, some of them, and then not so much others. Now, if it was the mobile phase, not so much, because the mobile phase is just going through. You see what I mean? Mobile phase is just going to be carrying everything through. And in fact, what would be a special property of the mobile phase? It needs to push everything through. What's the word for it? What you're looking for starts with an A, analytes. Your analytes all have to what in the mobile phase? Dissolve. Because if they don't dissolve, the mobile phase can't move them. Do you see what I'm saying? If your analytes don't dissolve in the mobile phase can't do its job. Mobile phase is just to push things through. So the magic happens in the stationary phase in a number of different ways. Okay, for our stationary phase is what in this case? Andy, what is this stuff? No, that's our analyte, or that's our mixture. What is this? Paper. This stuff is paper. Paper is my stationary phase. Well, how can paper separate out, be where the magic happens, where all these different components and the vis-a-vis markers separate out? Well, let's back up. Mobile phase, since we talked about that first. What mobile phase are you going to use for this vis-a-vis markers? Water. Why would water be good? Because it dissolves them all, because they are all vis-a-vis markers, right? So water is going to be our mobile phase. I got a bunch of it. Does it have to be pure? Yeah, it just has to dissolve. It can be a mixture. We could dump some ethanol in here too, whatever. Just, right? Okay. In fact, changing the mobile phase is a whole nother parameter of chromatography. You can really help things out by changing the mobile phase, but we're not going to. We're just going to stick with water. Okay. Stationary phase. We're using paper. There's a hint up here, if you've seen these images before, how paper is going to do its trick to separate out all the little components in the vis-a-vis markers, the different ones. How's the paper going to do it? Right? What is, where did my little marker go? Oh, I took it and pretended it was a vis-a-vis. What is this image? What is that? That's paper. Now, you biology people, you should have looked at, by this time, paper under the microscope. Hopefully you have. Hopefully you've stuck a lot of stuff under those microscopes and looked at them. Okay? Stuff like paper. Now, this is really much more zoomed up than you're going to get with an optical microscope. This is STM, scanning, does anybody know? Tunneling microscopy. So electrons are doing energetically impossible things to get these images. Maybe you've seen pictures like bed bugs and things. Everything's always black and white, and they have these images of very, very tiny objects. Anyway, so this is what paper looks like. How's that going to do anything? What's that? Filter. Very good. What is it going to do? How is it going to separate out the components of the vis-vis markers? Filter is a good word, but filter by what? By masses, kind of. Size. Look at the different size holes, right? Which components, which analytes in these vis-a-vis markers are going to get through first, get through the paper first? Well, they're all water soluble because they're all vis-a-vis markers. Otherwise, if a vis-a-vis marker had water insoluble components, you couldn't get it off the overhead transparency. The smallest ones are going to pass through fastest, right? In fact, it's an odd thing. Since vis-a-vis markers have all these different components, and they're all, right, soluble in water, do you think they have equal solubility in water? I wouldn't think they have equal solubility in water. And I would think that would complicate things, right? I would think that the things that have the most soluble in water, and they're the smallest, get through the first. That's not how it is in chromatography. In chromatography, you just need some degree of solubility in that mobile phase, and it's going to work. What slows things down is not solubility in the mobile phase. If you're somewhat soluble in the mobile phase, good, check, you're done, move on. What's the affinity, the chemistry is all happening here at the stationary phase. Okay, so if it's somewhat soluble, done. Mobile phase will work. The degree of solubility doesn't matter. Okay, so now I'm going to be dumping water in those beakers. What's the difference between what the mobile phase is doing, what I'm going to do, and what the mobile phase is doing here?
It's traveling down this, maybe traveling up.
Yeah. In this one, I'd have to be sitting there with the beaker or whatever and keep dumping it up on top. Constantly dumping. Here, I'm just going to dump it in the bottom down here, kind of get it up to the paper. Then what? The paper absorbs the water, yeah. The water travels up due to Jeffrey. What property of liquids allows this to happen? Starts with an S. Now, yeah, it's called capillary rise action and stuff, yes. But it's really due to the what of the liquids? There's an S. Surface?
Tension.
Surface tension. Surface tension. Okay. Get some in here. Now, is this going to be a fast process or a slow process? Slow, so we're going to keep going here. Marlena's just going to sit here and stare at it the whole time. But that's okay. Okay. Now, some of these, they were permanent markers. What's going to happen? They're not going to move. That solid line should just stay there, right? Should. Okay. So you, I think, can answer some of these questions. But it's technical jargon, so we maybe not. Desiree, all chromatographic methods separate the blank from the blank. You remember what you're after. What was the technical jargon for what you were after, chemically speaking? There's an A. The analytes. Separate the analyte. Okay. Now I'll actually accept two words for the next one. Maybe three. You want to think of one? From the solution. I think that sounds good. Now I accept four. Matrix. That's a really good one, right? I think that's the best answer. Or you might say solvent, or you might say mobile phase, or solution or mixture. All those would work. I think matrix is awesome. Okay, because matrix is about as general as you can get. How about the next part, Brandy? The blank phase transports the sample through the blank phase. Good. The mobile through the stationary. Okay. Elution chromatography. Kelly is, ooh, look, it's starting to happen. Right, the magic is happening. Elution chromatography. What is elution chromatography? Is this elution chromatography? Where'd Kelly go? I think that's a tough question because we are kind of constantly adding mobile phase. And that's what elution chromatography is. Here they're physically continuously adding their eluent, or the mobile phase at the top. And here we are kind of too. I mean, I'm not really adding it all the time, but if it wasn't there, I wouldn't keep going up, right? But so that's what elution chromatography is. You constantly are adding eluent. In elution chromatography, what makes A and B go down the column? So you started with, see, here's time 0, right? Here's time going this way. Here's time t equals 0. So you have a little detector at the bottom, and it's not detecting anything. So the signal's 0, right, at time 0. And here's time 0. So you dump A and B together up at the very top. In elution chromatography, Jeff, what makes A and B go down the column? Gravity, yeah. Gravity is making the, I'd say that's a good answer. Gravity is making everything go down, but it's a little more complicated because gravity's pulling the mobile phase down, but then your A and B have to be somewhat soluble to some degree in the mobile phase for it to be pulled down by gravity, right? But all that works. What's in the column? Ida, what would you guess is in the column? At the very end, notice how as time progresses here, these A's and the B's components, they're starting to separate. They're starting to travel down the column at different speeds, and by, what is that, T, can't even see that. By T3, looks like things are actually, man, even by T2, things are getting pretty separated. What would be in the column? What could be in the column? Pretty much you try it. This is what I think the word chromatography is very often thought of as a verb. You try it. Silica gel, leaves, cotton, t-shirt, whatever, hair, anything. You try it. You try it. Now, it's kind of good to have some idea, especially if you have some understanding as to what you're after. Like this is a great thing, right? All those little holes and gaps separate by size. Okay, but what's in the column? It could be anything. Ground up chalk. Okay.
You said try it?
Yeah, but you know they've moved way on from there. So now there's better answers than just trying it. The guy who first tried it, I don't remember if I'm jumping ahead or not. The year, I don't remember, 19, yeah. Anyway, I won't say the year because I don't remember for sure. But the guy is, this is what I just imagined, because I don't know how people jump from this to what they actually did. He sees all the leaves changing colors. So he figures all those colors are in those leaves. And they had some compounds like ether and things like that. So what he did is he took all these leaves, put them in a pot and just, smashed it and got all this juicy stuff. And then he put it on the top of this tube and he ground up calcium carbonate or chalk. And then he got all these pretty colors, all the chlorophylls. What possessed him to do that, right? So that's where I'm coming from. Try it. He must have thought again, how do you go from that idea to actually trying it? He's like, that's what a genius does, and I don't see how they're connected. But he figured it out, and he did it. He got all the pure chlorophylls out in the end. So, and that's where liquid chromatography really got its historical start. Anyway, chromatogram. What's that? Do you see that up there, Gloriana? A chromatogram? Here's a chromatogram. It's a graph, exactly, of what the detector sees over time. And here it is. Here's our chromatogram. Notice it's always detector signal versus time. That's your chromatogram. At what time, now when I say at time, you've got T0. I should probably write it so you can see it. You've got T0, T1, T2, T3, and T4. So these are just static images taken at these different times. At which time, Ricky, would you say A and B start to separate?
I would say T0.
Yeah, the argument, I would agree, because they got to be starting to separate from the very beginning. I mean, you could argue T1, but man, they started to separate right when you initially dumped it in. Okay, because they're traveling down the column. So there's no really right or wrong answer. It's more like a concept. Now here there's a right or wrong answer. At what time does A come off the column? Or what time does A elute, Danielle? What would you say? What time does A come off the column? I think it'd be easiest to look at the chromatogram to answer it. Because here's A. Yeah, it's somewhere between T3 and what they want you to do is they want you to see the highest point. Whatever the highest point is, you come down and you read the time. So that's a T3. So that's how you're supposed to read these. They call them retention times. And that's probably more information than you need right now, but that's the idea. Okay. How about B? We said would be T. Everybody T4. Let's say B. Those are the retention times. You know what's kind of interesting? This is the real power in chromatography, and this is where it gets really expensive too, is the retention times. For this to be a real useful technique, would you want the retention time to change? In other words, you're going to analyze somebody's blood for cocaine, and you're earning all these big bucks because you know how to operate a high-performance liquid chromatograph with mass spectral detector. And you know cocaine comes off in somebody's blood at 2.8 minutes. If it always came off at 2.8 minutes, you know how much easier your life would be? You see a little peak at 2.8. Ah, old man, bad boy. Is that how nature works? Would it always be 2.8? As long as you don't change anything in your run. Don't change anything. And cocaine will always be out at that same time. The retention times won't change. Like if you do this experiment tomorrow, you don't change anything, you get the exact same chromatogram, exact same retention time. And maybe if your sample is a little bit different, you might have more or less A and B, but A will always come out at T3, B will always come out at T4, as long as you don't change anything. What could you change? Well, you could change the mobile phase composition, you could change the length of the column, right? There's a lot of things you could change. Change the diameter, okay, there's a bunch of stuff.
What if like that person had alcohol in their blood and they didn't drink a lot of water, so it was a little thicker than usual, or something like that? Do you think that would change?
So if good question. You change the sample. Oh, no longer is it leaf extract. It's leaf extract mixed in with someone's mess of whether beer or wine, whatever. No, it doesn't matter. Cocaine or whatever the analyte will be will always have that same retention time because it's the analyte that matters, not the original mixture. So that's the real power in this chromatography. Again, these are ideas for all types of chromatography, no matter what the name is. Which compound A or B spends more time in the stationary phase? Desiree, what would you say? Which compound A or B spends more time in the stationary phase? Right, they're passing through it. They had to spend some time in the stationary phase. B, yeah, because look at B came out at, I don't know, 10 minutes, and A was 8 minutes or something. Yeah, so B spent more time in the stationary phase. Which compound spends more time in the mobile phase? Randy, what would you say there? She's thinking. That's good. Because if you realize B is spending more time in the stationary phase, that's why B came off so much later, right? It actually stopped. It got, in this case, well, in our paper chromatography case, it actually physically got blocked, right? It's hanging out, hanging out, hanging out, and then it's moving again. And then it's hanging out, whoop, it's going up, right? It's going up. Gets stuck, and then it's moving again. Whenever it's moving, it, meaning anything in the mixture, it's always moving at the same speed. Moving at whose rate? The what's making it move? Mobile phase. And the mobile phase, in, for example, with paper chromatography, it's just whatever rate the water's oozing up there due to capillary rise or surface tension. And here, with this diagram, it's just whatever rate the mobile phase is dripping down through. If you're not stuck anymore, or in this case it's a little bit different, but either you're adhered or chemically absorbed or physically obstructed, whatever's going on with that stationary phase, either you're stopped or you're moving. If you're stopped, well, you're stopped. If you're moving at the mobile phase flow rate. So everything spends what in the mobile phase? Same amount of time. Everything has to spend the same amount of time in the mobile phase. That's the only time you can move. Seven. Kelly, how about 7? Is there more of A or more of B? What would you guess? I would guess that's a good guess. There's more of A, but it's a trick question. And I like how she said A because A's peak is bigger, right? It gave a lot bigger detector signal. But you don't know what the detector was. What if the detector is, okay, I'm going to detect the color red. So what's the complementary color of red? Green or something, right? So it depends on the degree to which green absorbs. So different compounds, right, they give different signals depending on what the detector is. So A just might be super sensitive for whatever you're detecting. So A's peak is going to be huge, and while there might be a lot of B, it takes a lot of B to give the same signal. So it's a trick question. You don't know. Is there more of which one? You would have to make a calibrate. You'd have to inject known amounts and see what this area is under A and know what its concentration is. See what the area is for B and know what its concentration is. Make a little calibration curve and then inject different amounts, and then you can tell, get a rough estimate. How about this? In all chromatography methods, do you get pure A and pure B at the bottom of the column? Pure A and pure B? Jeff, what would you say? What else would you get? It sounds like you shouldn't, right? Because it sounds like in life you shouldn't get something for nothing, right? I feel like I should say no too, but it's pure. You want to, there's no secrets anymore. For example, with vis-a-vis, you could, this is kind of a cheap way of doing it, but you get a longer piece of paper and you get these bands that start separating out. You could take a scissors and cut them off and get the pure yellow pigments, green pigments, and you'd have whoever's manufacturer's pigments there. Go up to room 415 where all these fancy chromatographic instruments are. Inject Coca-Cola. You get all the pure components of Coca-Cola. There's no secrets anymore. Everybody knows what this stuff is, and you can make it. You just better not sell it. Right? Okay. Yeah, so you definitely get pure A and B. Are A and B more dilute or concentrated when they come off the column in comparison to when you started? What does it look like there, Ida? What would you guess? Would things be more concentrated or more dilute when you get done? We get this pure A and this pure B, but they're more dilute. They are really dilute. They're really dilute, okay? They're really dilute. And that's a consequence of, again, of all chromatographic methods. What else could the x-axis be? So we have the x-axis being time. Anybody have an idea what else it could be? Well, oh, I can see. You're saying concentration of A or something, maybe? Yeah, that'd be a complicated one to have it be, because you'd have 0, 0, 0. But it would look. Oh, yeah. Then the plot would look different, though. I think the plot would end up looking different if you had the x-axis be concentration. I was thinking just the volume of the mobile phase that you added. Right? Like you're dumping in, I don't know, 3 mils a minute or something. So after 10 minutes, there's 30 mils, and you just keep on going. So it'd just be, because you add the mobile phase at a constant volume per unit time. So maybe mobile phase amount. But time is just just leave it at time. Don't even mess with that. Which compound A or B is more soluble in the stationary phase? Now we're getting into some chemistry here. Danielle, we got number 11. Which compound A or B is more soluble in the stationary phase? A. Do you agree, Gloriana? So if something is soluble in the stationary phase, what's the effect? It's really adhering really well to that stationary phase. It's not moving very often, right? Because it's really soluble in the stationary phase, right? It comes out of the mobile phase and it sticks. Or with sides exclusion, it stays there. So the compound that comes off what is the most soluble in the stationary phase? The compound that comes off first or last? Last. The guy who comes off last is the most soluble. Like dissolves like. Or in this case, the guy that, with paper chromatography, here's a nice one. Would you say that the yellow dye is physically bigger or smaller than the blue dye? It's physically bigger, right? Exactly. If you see that, then you're seeing what we're trying to say. How about the mobile phase? Which compound A or B is more soluble in the mobile phase, Brandy? It's kind of a trick question. Remember we said that we really don't care, because chromatography is going to work as long as they're both somewhat soluble. So you really don't know. You don't know. You just know that they're both soluble because they both moved. So you have no idea which one's more soluble in the mobile phase. Nor do you really care. They just got to be somewhat soluble. Another way of saying the same thing, kind of, is which compound A or B is more strongly retained in the stationary phase? Anybody? B. Yeah, it's another way of saying the same thing. Are compounds A and B of homogeneous concentration throughout their respective purely separated bands? So you collect this stuff. There's A, there's B, you collect it. So it's sitting there dripping, right? You're collecting it. So I guess you'd put the beaker down there right around this time to start collecting A. That's where you'd put the beaker down there. Otherwise, you'd get even more mobile phase. You put the beaker down there, it's dripping. And then remove the beaker when you hit this, pretty much. Do you get the same concentration per drip of A? No. When would it be the most concentrated? Right at T3, right at the peak there. So it looks like in these, they call these bands. They call these bands. All right, if it's going down, I don't know, it'd be the most concentrated in the center, and then I can't draw a lighter, but lighter concentrated as you go out. Okay, they're most because it's identified right here. There's the concentration gradient. It's most concentrated in the center. So are compounds A and B of homogeneous concentration? You'd say yes or no. Homogeneous means same throughout. So are these compounds have the same concentration throughout their band? Definitely no. They're most concentrated in the center. Okay. How would the chromatogram change if the amounts of A and B were doubled in the sample? So I guess I should have one here. Here's our signal and my time. What did it look like? It looked kind of like something like that, right? And then I double. What would happen? Exactly how much bigger? Twice. So now whether things get more, the degree to which they get higher or not, I guess what I'm trying to say is that's area. The area under the curve is exactly doubled. You don't know if it's going to be higher, sharper, whatever, but the area under the curve is going to be doubled. So whatever you draw over here, oh, and what should also change? How will this, when you draw this with doubled area, you center it where? Center A's peak over T3 and center B's peak over T4. So make sure you do that when you sketch it in here. So wherever T3 was, have a double-sized peak, and whatever T4 is. So T4 doubled. Now they might start overlapping here. All right, they might start overlapping somehow, but just end up doubling your area. But make sure the peaks are still centered over T3 and T4. Zone broadening. So zone broadening is just the technical jargon for why don't you get, over, let's draw an idea here. Detector, time, detector signal, trying to draw the axes on a chromatogram. And then we said at T3 and T4, why don't you just get, wow, still has a peak, a really high line. Right? Why are there widths to these things? And some are wider than others. That's all about zone broadening. And zone broadening has two types of diffusion. That's why you get these peaks. And the more diffusion, or the more zone broadening, the fatter these peaks get. And fat peaks are a bad thing. Right? You want these sharp, narrow peaks. So there's two types of diffusion. The picture's trying to illustrate one of them. You see what it's trying to illustrate? Andy, you see what it's trying to illustrate? Why you have the peak on the left, and then it ends up getting fatter on the right. It's because of a certain type of diffusion, and why would it be getting fatter? What's this 1, 2, 3 thing? Not detector. What are these blobs that they're trying to draw on here? This whole thing, first off, is the what phase? Yeah, that's our, good. If you recognize that, you're on the right track. That whole thing right now is our stationary phase. And then these little blocks in here, you can see them, and they're all these different shapes. That's, again, the stationary phase. And it could be acting like a filter. It could be acting like, if it's size exclusion, It could be the guys could actually, it could be coated with some material and then like dissolves like and change that coating. But that's what your stationary phase, what they're trying to say in this case, what the stationary phase is made up of. It's made up of all these packed stuff. You really don't know what it is. But 1, 2, and 3 are supposed to be different paths, where there's some paths that are longer than others. And they're just trying to say that because these guys that whatever you packed your stationary phase with, you didn't do a very good job. I mean, maybe you want to use chalk. So you're in a rush, right? And the goal of labs is to get out as fast as you can. So you take some chalk from the chalkboard. You didn't smash it up very good. Some are big chunks, some are small chunks. And then you pack it in your column, and then you try to do the chromatography. And you get these big fat peaks because there's all these different paths. Some paths are short, some are long, and you're kind of defeating the purpose of what you're trying to do. So you didn't get this nice packing thing going on. And that type of diffusion is called eddy diffusion. Right? There's different paths through the stationary phase. So even though it's all A molecules, for example, right? The column did its job, but the point is these different A molecules are traveling different paths and all in the same column. And that's hard to stop. It's really hard to stop. But you fork out big money to try to stop it. And we'll talk about later on how they're trying to figure this out and how they're improving matters. Then there's one more type of diffusion. Anybody know what it is? A hint is number 13. When you have a band, right? Where did we say it's the most concentrated? Oh yeah, peak, you're right, in the chromatogram at the peak, right? But then when you think of a band, you're supposed to kind of flip it on its side and look at how this thing is traveling down the column, and yeah, it's the most concentrated in the middle. So what does nature do? Things diffuse from where to where? High to low. Well, if it's most concentrated in the center, it's going to diffuse in both directions. High to low concentration. You can't stop nature. That's longitudinal diffusion. So both ways. Diffusion happens both ways. Just essentially from diffusion from high to low concentration within the band itself. Even though it's nice and purely separated, it simply gets fatter and fatter as time progresses because, right, that's just what nature does. Nature, things go from high to low concentration, they diffuse. So there might be so diffusion bad, right? Zone broadening bad. What would be an easy way to decrease, I think this is the last step, this is it, to decrease the effect of each type of diffusion. So we've got eddy diffusion, and we've got longitudinal diffusion. All right, so let's just see if we can name some things. We'll name them up here, and then we'll put a big X in there if it actually helps or not, or a check mark or something. All right? What could be something that you could do that might actually influence this stuff? Who am I picked on? Monica, I haven't picked on you. What could you do to this whole process? Now, this whole process, you can think of it, I guess, this picture. You could think of this type of picture, but because chromatography is happening in both of those. What's something you could do that might have an influence on this stuff? It's a hard question. I think it's hard.
I guess have a stationary phase that doesn't have, that it's uniform.
Ooh, uniform, really uniform packing, right? That's a good one. Make the packing really uniform. Okay, would that help eddy diffusion? Yes. Would it help longitudinal? Not really. What helps longitudinal? If you want to decrease longitudinal diffusion, you need to decrease what? The amount of... Well, yeah, kind of. But time. Time is key to go from beginning to end of your run, whatever it is. If you can decrease the time, you can decrease longitudinal. So that might help you answers, put in some possibilities here. Jackie, what could you do? What's something else you could do? I don't have a... Maybe this is the tube. You have to imagine. This is the tube that we jam chalk in. Well, instead of making it this length, what happens if I just use half of it? Right? That would be what? Shortening the stationary, or the column. Let's shorten the column. Shorten the column, right? It contains the stationary phase. Containing stationary phase. Would that have any influence on eddy diffusion? Mel, what would you say?
Because it can change the path length.
I think so too. It can change the path length. So now it didn't really do a whole... I think there's less degree of paths, right? But the real influence is on longitudinal because it's shorter. So I would argue yes for both, but maybe not so much here. Anybody think of anything else? How about change the mobile phase, right? That's a good one. Change the mobile phase. Any influence on eddy diffusion? Yeah, it'll influence longitudinal because it'll influence the amount of time, maybe, right? I guess in this case, capillary rise action, does that change with, I suppose it would change with, the speed would change with surface tension, I would think. I know the maximum height would definitely change. Eddy diffusion is more of a property of the stationary phase. So I'm not sure you could say anything about eddy diffusion. And maybe you could even say anything about longitudinal diffusion if what didn't change? The time. So maybe instead of mobile phase, let's change the mobile phase flow rate. Now, it would definitely influences which one? Longitudinal. And probably not eddy. It's probably an easier way to think of it. Okay? So that's enough. Let me get your exams back.